In this video, I want to describe the double-slit experiment, but by using path integrals. And at first, we will introduce all the important equations. Then I want to give you the physical intuition with a certain application of that. So we will apply the formulas that we see in this video. Let's start. So we consider a plate in the x direction with two slits. So this is the x direction, and let's assume that the center of this slit here is x1, and the center of the second slit is x2. So we assume that the slits have the same properties, in particular the same aperture, the same gap. Let's call it delta. This is delta. And now what we need to do is we need to think in terms of wave functions. So we assume that we have a particle, and the particle is described by some wave function. So the particle is a particle of mass m, and we can think that the particle is very likely in either this slit or on this slit at some initial time that I can call t0 equal to 0. So at time 0, the particle can be either here, somewhere here, or somewhere here. But we need to think of this in terms of amplitudes due to quantum mechanics. So we have an initial amplitude, and then there is a propagation from either this slit or this slit towards, let's say, a wall. So we can call this a wall, but it can be a device, whatever we want. So you can think that this is a wall, and we reach the wall at time t equal to tf, and let's say that this is the direction of y, and the wall is located at y equal to yf, so at the final y, let's say. Now we need to write down some equations, and in particular we assume that there is some kind of distribution here around this slit, and the same distribution will be here around this slit on the left. So we have some distributions that we think of Gaussian, we think of as Gaussian distributions for simplicity, because in that case the integrals can be computed quite simply, and therefore what we can write is something like this. So the probability, so this is a probability, it's not the probability amplitude, it's the probability itself, and the probability would be a function of x, y, and t, because we have 2 dimensions of space and 1 dimension of time. But now I'm interested in the probability at y equal to 0, so let's assume that this is y equal to 0, and at t equal to 0, because this is the initial probability, the one that we have on this plate with the 2 slits. And I'm going to write it like this, and then I will also explain that to you. It's quite easy to understand, but let me write 1/2, and then we have 1 over the square root of 2 pi sigma squared, and then we have the exponential of minus x minus, let's put a tilde under this x1 and x2, and you will understand why, because I don't want to get confused when we carry out path integrals, so I will put this tilde. So we have x minus x1 tilde squared over 2 sigma squared, and then we have plus 1/2 1 over the square root of 2 pi sigma squared. So this is the variance of the Gaussian distribution, sigma squared. If you want, sigma is the standard deviation, and we can think that this sigma here is of the order of the gap, of the opening, or the aperture, whatever you want to call it. This delta will be proportional to this sigma. We can choose sigma to be delta, and maybe we can do that later, but for now we can think that sigma is of the order of delta, They do not necessarily need to be equal, but we can think that this is the case. And then here we have the exponential of minus x tilde 2 squared divided by 2 sigma squared. So in principle, these two standard deviations could be different, but for simplicity, we assume that they are exactly the same because the two slits have the same properties. And the probability to find a particle here, the maximum here of the Gaussian distribution will be the same as in here. So we try to think in terms of some symmetry to simplify the problem a little bit, but it can be generalized quite simply, quite easily. Now, it's not too difficult to understand this choice for the initial probability density, right? So we have a probability density, and you can check that if you integrate it over x from minus infinity to plus infinity, the first integral over this Gaussian distribution will give you 1. So we have 1/2 times 1 plus 1/2 times another 1 coming from this distribution here. So this will be 1, and it means that these factors of 1/2 will simply normalize the distribution. Then there is some non-negligible probability also in between the slits. If you just check the mathematical expression, if you set x, for example, to a value that's here, you will get a value which is not 0 for the probability. But since this is an exponential which decays quite fast, and also this one, the probability will be close to 0 there. So it makes sense to reason in terms of this probability. It's not, of course, the only choice. You can choose this probability in different manners, but the fundamentals, the most important aspects of the double-slit experiment will arise by choosing this probability as well. So it is some kind of simplification, but it is still quite general. Now, at this point, we have to reason when we think of quantum mechanics or quantum physics in general, we want to reason by using probability amplitudes, not probability density. So this is a probability density, which is a real function. But in quantum mechanics, we have something like psi of x 0, 0. And then if we take the square, the magnitude squared of this probability amplitude, which is the wave function, you can think of that as the wave function, you get the probability of x 0, 0. And in general, this holds also if you have yt and yt here, which are not 0. And so we have to choose our psi such that the mod squared will give us p. And this is not too difficult, it's quite easy. And I want to show you one possibility, which is the following. So we take the square root of this, and then we sum the square root of this, but we have to multiply by a factor of I, by the imaginary unit, so that the two parts are independent of each other. So let me do it. We have 1 over square root of 2, then we have 2 pi sigma squared to the power of minus 1 over 4, which is simply the square root of this. And then we have the square root of the exponential, which we can write as the exponential of minus x tilde 1 squared divided by 4 sigma squared. So this factor of 4 is due to the square root of this expression. So if you take the square root of this expression, you have a factor of 1/2 inside the argument. So this 2 combines with this 2 and you get a factor of 4. Simple as that. Then, as I said, I multiply by I, and then I have something similar here, 1 over square root of 2, 2 pi sigma squared to the power minus 1 over 4, exponential of, let me zoom out, minus x tilde 2 squared divided by 4 sigma squared. Now, if you square this function, this probability amplitude, you take the mode and you square it, you can simply square this part and then you square this part. And this is thanks to this factor of I, which appears. So this is the real part and this is the imaginary part. Of course, you could have put the factor I in here, or if you want, you can also take this and multiply it by a phase factor of the kind e to the I phi. And the mode of this is just 1. So you can see that there are different possibilities, but at the end of the day, the calculations will still lead to a very general result. So I will take something of this kind, and we will not even be interested in these multiplicative factors, but I want to show you that little by little. And at this point, we are ready to write down a path integral. So what we want to write is the amplitude at the final point xf, the final point in y, and the final time tf. And this is something of the following kind. So we have a propagation over x. So we consider this dx factor. We have the factor dy in the path integral, and then we have e to the I over h bar, the Planck constant, multiplied by the action. And the action is the action for a free particle. So it will depend on x dot, the derivative of x, and also the derivative with respect to time of y. I will write down the action in a moment. So first, let me finish writing the expression for the path integral. Then we have some constant a, which is a normalization factor in the path integral, which we will not really be interested in determining this constant. It's not really important for what we want to do, but I will put it there. And then we have psi at the initial point in space, the initial point in y, and the initial point in time. So this is the initial point in x, if you want. You can see that this is not really 0. It can be any point on the plate. So it can be either one of these points. And not necessarily a point here in the gap, in the second slit, or a point here on the first slit. It can also be a point outside of that, due to the fact that there is a non-negligible probability to find a particle also in here, somewhere here. So it can penetrate through the plate. And of course, this is due to the strangeness, the weirdness of quantum mechanics, if we assume that the initial probability is of the following kind. And so this is the starting point. This is the path integral, and this is what we want to compute. Let me write down the action, which is a function of x dot and y dot. It's a functional because it depends on functions. And it is an integral from 0 to tf. So 0 is the initial time. We can just set it to 0. The mass of the particle divided by 2. And then we have the mode of the velocity squared. So we get x dot squared plus y dot squared. So we think that we are in classical. So I mean, we consider classical, let's say, quote unquote, classical velocities. They are not relativistic velocities. Remember that we also have to multiply by the differential of time. So here we have dt, and this is an integral of the following kind. So if we want to rewrite the amplitude, the final amplitude, by means of the path integral, we have something of the following kind. So you can see that we have a path integral over y, which is something like this, e to the I over h bar, m over 2, integral from 0 to tf y dot squared dt. And then we also have a path integral over x, e to the I over h bar, m over 2, integral from 0 to tf x dot squared dt. And the path integral over x will also integrate the function psi of x 0, 0, because this function depends on x. So it will appear inside this path integral. I will show you that So we can think of this like this. And then we also have the constant a, whatever. When we compute the path integrals, we need to discretize our continuous quantities. So in particular, let's start from the 1 over y, which is just the simplest part of the integration. Now, when we discretize the integral, we let dt go to some epsilon. So we think that epsilon is small but finite, whereas dt is infinitesimally small. And the function y dot will become something like this, yj minus yj minus 1. Or if you want yj plus 1 minus yj divided by epsilon. So this epsilon is the increment in time, and here we have the discretized part, the discretized function y of t. So instead of thinking of y of t, we think of y sub j, the discretized version of that. And therefore, the integral over y, so let me write down the integral over y, we have something like this. We have integral over dy1, and this y1 will be close to y0. Y0 is 0, if you recall, so we can think that here on the plate, the coordinate y is equal to y0, which is equal to 0. And to be more general, I can say that, y1 is very close to 0. It's the starting point of the integration. And since we start to integrate from this plate, we don't have to integrate also on y0. We have to start at a point which is slightly off the plate. Whereas when we integrate over x, I will show you that later, we also have to integrate over x0, which is the initial x, because we don't know exactly where the particle is located at first. So we have to integrate over all the possibilities. And this is quite intuitive, even though it can, of course, it can be confusing at first if you don't think about it. But I will say that once more later. Then we have to integrate over y2 dot dot dot, and then we integrate over yn minus 1, and we have to think of this as a point which is close to, and also this one was close to, this is close to yf, which is the final coordinate. So when we reach the final point, but we don't have to integrate over yf. And it is still quite easy to understand that, because you can see that this is a function of yf. So we cannot have an integral over yf there on the right. Yf is something fixed. Even if we can consider this to be a function of yf, so yf can be any number, but we don't have to integrate over yf on the right, because otherwise we get something that doesn't really make sense. We have to integrate over all the points in between. The integral over x, as I said, will be very, very similar to this one. There is just one addition, and the addition is that we have to integrate also on x0, and all the others will be x1, x2, and xn minus 1. And I will get to the integral over x later. Then we can rewrite the integral, so the path integral here by factoring the exponentials in the following form: e to the I m over 2 h bar, and then we have y1 minus y0 squared divided by epsilon. Then you have something like e to the I m divided by 2 h bar y2 minus y1 squared divided by epsilon, and you get the pattern. So dot 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 e to the I m divided by 2 h bar yn minus yn minus 1 squared divided by epsilon. And this yn will be equal to yf when you take the limit. Now we can carry out these integrations, but in order to do that, let me introduce just one formula. I will not prove it here, it is quite straightforward to prove, but I will take this for granted. I will use the following formula. So the integral from minus infinity to plus infinity of the product of two Gaussian terms of the following kind, e to the a x1 minus x squared, e to the b x2 minus x squared dx, this is equal to the square root of minus pi divided by a plus b, e to the ab divided by a plus b, x1 minus x2 squared. And this holds for the real part of a plus b less than or equal to 0, and a plus b not equal to 0. So you can check that indeed these properties are satisfied, because in our case we have that a and b are both imaginary, because here we have the imaginary units, and of course a plus b is not equal to 0. Although we have a real part of a plus b equal to 0, but you can see that here we have less than or equal to, so the equal sign is also acceptable. Anyway, we have to use this formula, and we can start, for example, by integrating over y1 first. So when we integrate over y1, we have to integrate over these first two terms. And you can see that we have indeed an integral of this form to carry out. So let me write. We have integral over y1 e to the I m divided by 2h bar epsilon y1 minus y0 squared e to the I m divided by 2h bar epsilon y2 minus y1 squared. What we get is a constant that I will not write. I will not bother to write it, even if it's quite simple. And then I have e to the I m divided by 2h bar 2 epsilon. So we get this factor of 2 if we use the formula that I gave you there. y2 minus y0 squared. So you get the final point minus the initial point, y2 minus y0 squared. You don't get y1, of course, because we have integrated that out. And similarly, we can carry out an integral over y2 after integrating over y1. So when we integrate over y2, we get something proportional to this integral here, integral over y2, e to the I m divided by 2h bar times 2 epsilon y2 minus y0 squared. And then we get e to the I m divided by 2h bar epsilon y3 minus y2 squared. This is the subsequent term in the product of exponentials that I wrote earlier. And still, if we apply this formula here, and in our case, this formula could look even simpler if you want to simplify that, because you can see that, for example, in the first integral that we carried out, we had b equal to a, whereas here, if we call this b, this one here would simply be b divided by 2. So the formula could simplify even more. Although that's not necessary, you just use the formula. So this would be proportional to, let's just write proportional without writing the constant. This is proportional to e to the I m divided by 2h bar 3 epsilon y3 minus y0 squared. So you get a factor of 3 in this case. So you get the pattern, right? If you carry out the integral over yn minus 1, I will not write it, you have e to the I m, something proportional to this, e to the I m divided by 2h bar n epsilon times yn minus y0 squared. And when you take the limit, of course, as I said earlier, yn is equal to yf. And n times epsilon, what is that? That is simply the difference in time, Tf minus T0, but T0 is equal to 0, so that's just Tf. That's the overall time that it takes for the particle to travel from the plate to the wall. And therefore, this can also be written as e to the I m divided by 2 h bar Tf yf squared. Now, at this point, we need to carry out the integrals over x, and this can be done in a very similar fashion. The integral will look like this. So you have an integral over x0. So we have this additional term, as I said earlier, because we don't know exactly where the particle is located at first. We have to integrate over all these possible points over x because we don't know where the particle is. Whereas when we integrate it over y, we know exactly where the particle starts because it starts at one of these points, but the coordinate y is equal to 0 there. So that's the reason. Then we have dx1, dx2, dot, 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 dxn minus 1. So in this case, we don't have to integrate over xn because remember that xn is equal to xf. So it's the final point on the wall. And we don't have to integrate over that because the wave function depends on xf. So we cannot integrate on the right over xf because xf must appear. We don't have to integrate that out. Then, of course, we have the same exponential factors of the kind e to the I m divided by 2h bar. And then we have epsilon x1 minus x0 squared. Then I will write only the final one, e to the I m divided by 2h bar epsilon xn minus 1 squared, like this. And so this is very similar to the one that we wrote for y, which is here. But remember that now we have an additional function. So the function that we have here is psi of x00. We called it psi of x00. And the function psi of x00 is composed of two terms. A term proportional to this exponential and a term proportional to this exponential, right? So we have two similar integrals that we have to carry out. One that integrates this exponential here inside the path integral, and the other one that needs to be integrated is this one. But the form of the two integrals will be the same. So we can just bother to write one of them, and then of course we can easily guess how to integrate the other one because the form is exactly the same. So the path integral over x will be proportional to something like this. Here I'm going to write e to the minus x0 minus x tilde 1, but of course when you integrate over the second slit, instead of x tilde 1 you have x tilde 2. Simple as that. And then here we divide by 4 sigma squared. And of course we have some proportionality factors. Here we have the factor a, and there are other constants that appear, but we are not really interested in those constants because when we want to take when we take the magnitude, we have some constant factor, so we have some complex number here, c, then we take its magnitude squared, but this will just be a constant, and it is just a scaling factor that we might avoid writing down. It's not necessary. So this is the path integral that we need to carry out. If we integrate these terms, if we only add these terms, the integral would be exactly the same as the 1 over y, but we have this additional term here that contains x0. You see here, right? But if we carry out the integrals over 1, over 2, and over n minus 1, so over x1, over x2, and over xn minus 1, if we carry out these integrals first, we get the same result that we got over y. So if we integrate over this first, we have only these terms to integrate, right? So if we carry out this integration, we will have something proportional to this, but instead of yf, of course, we have xf. So we have e to the I m over 2h bar tf xf squared, something proportional to this, but I don't bother writing down the proportionality constants, as I said. So we are left with just a simple integral over x0, where we have to take the multiplication between this exponential, which contains this imaginary unit, and this exponential here, which is not an imaginary integral, as you can see there. So, sorry, an imaginary exponential. This is a decaying exponential, whereas this is just an oscillating factor. There are conceptual differences between them, but when we integrate over x0, the integral is still in this form. If you check, the integral is still in this form, and therefore we know how to integrate that. We don't bother writing down this proportionality constant, we just want to write this factor here. And if we do that, we get something which is proportional to, so let me write it here, we get something that is proportional to the exponential, now let me write it like this, exp of 1 divided by 2h bar tf over im minus 4 sigma squared xf minus x1 tilde squared. So I have simply rewritten this factor like this, 1 over b plus 1 over a, which is the same. And what you get is exactly this. You call one of these terms, like minus 1 over 4 sigma squared, you call it a or b, whatever, and you call this one b or a, vice versa, right? And this is what you get. So if you want, we can rewrite it in a different fashion, in a different form. So we can write it like this, exponential. We can multiply by the complex conjugate of this on the numerator and the denominator. And what we get is something like this. We get 1 over 4 sigma squared plus 2h bar tf over m. And we have to square it. Then we have 2h bar tf over minus im, because we have to take the complex conjugate of this, or if you want, we can write it like this, m times I, which is the same. This I is like a minus I in the denominator, if you think about it, right? Because 1 over minus I is equal to I, because you get minus I squared equal to 1, which is true. And then you have minus 4 sigma squared times xf minus x1 squared, like this. Now, we can also we can write down the final expression for psi of xf yf tf, which will be some complex constant that we will write as b. And then we have the exponential, this exponential here. So let me just simplify it a little bit. So let me write this as exp of let's call it I don't know, f, capital F, which is a function of, let me write it as a function of xf and x tilde 1. And then so let me write it here as well, f as a function of xf x tilde 1, and then we have plus I. This factor of I, remember, comes from the fact that the second Gaussian term in the initial amplitude, where is it? It's here. So this second Gaussian is multiplied by I, and I will keep it there because it's simple. I have I, and then I have the same exponential of the same f, but instead of computing f at xf x1 tilde, I have to compute f at xf and x2 tilde. Multiplied by, remember, we also have a factor that depends on yf, e to the I m divided by 2h bar tf yf squared. But this is just a phase factor, so when we calculate the probability amplitude, we have to take the mod squared of this function. But as I said earlier, the mod squared of b is just a scaling factor, which we are not interested in. But the mod squared of this expression is just a 1. So we will not be interested in this. The thing that we are interested in is this one. So the mod squared of this expression. That's what we want to do, and that's the final part of. That's the final part of the theory. So of the formulas that we need. Then I want to show you some graphs in Matlab. I will use Matlab, but it is simply just the formulas that we see here, and we do some applications of them. We consider some applications of them. So in order to do that, first let me rewrite this first exponential as z1 and this second exponential as z2. We are interested in the mode of psi of xf yf tf squared, and we have to remember some properties of complex numbers. So we have the mode of b squared. As I said, we have the mode of this squared, but that will just give us 1 when we take the mode. And then we have the mode of z1 plus I z2 squared. So we need to remember how to take the mode squared of a sum of two complex numbers written like that. But that's quite simple. So we have mode b squared. The mode squared of a sum of numbers like that, it is simply equal to the mode squared of the first number plus the mode squared of the second number, which is just the mode squared of z2, because the mode of I is just 1. Then we have plus the first number multiplied by the complex conjugate of the second number plus the complex conjugate of the first number multiplied by the second number without complex conjugate. And this can also be written as twice the real part of one of these. So we can take, for example, z1 star, which is the complex conjugate, times I times z2. And now we can apply these formulas. And in particular, I will write, for example, I as e to the I pi over 2. So this can be combined with these complex numbers. And I want to write z1 and z2 in the following fashion in particular. So this would be, for example, z1, and in order to simplify the notation there a little bit, we can also write this in the following fashion: the exponential of a plus ib times xf minus x tilde 1 squared. And you can easily check that a, for example, would be minus 4 sigma squared divided by this denominator, whereas b is simply equal to this number divided by this denominator. So it's quite easy to check. And Z2 would simply be the same as this one, but instead of x tilde 1, we have x tilde 2. Simple as that. So we can rewrite this expression in the following way. We can write that as mod b squared e to the a xf minus x tilde 1 squared. This will be just the mod of z1 squared plus the mod of z2 squared is just e to the a xf minus x tilde 2 squared plus, now let me go below, I have plus e to the a xf minus x tilde 1 squared plus xf minus x tilde 2 squared. So here I'm taking, I need to take twice the real part of this product. And then I am left with twice the cosine of minus b xf minus x tilde 1 squared plus b xf minus x tilde 2 squared plus pi over 2, which remember comes from this phase factor here. And then we have to close the bracket, this bracket here, but you get the idea, right? Now we are ready, we are actually ready, but before proceeding, let me just introduce another symbol which is convenient to rewrite the expression. So x tilde 2 is equal to x tilde 1 plus delta. This is a definition for delta, where if you check, this is just the distance between the centers of the slits. So here we have x2, here we have x1, and this distance here is delta, capital delta. Remember that we use the lowercase delta for the width of the slit, for both of them, because they are equal, they are the same slit basically, but with the same width. And this capital delta is something that of course should be larger. This capital delta should be larger than the width of the single slit. And I want to write the expression here in terms of capital delta. So if we do that, we have something like this: mod psi of xf yf tf squared equal to mod b squared, and then we can factor out something like this: e to the a xf minus x tilde 1 squared, and then we have 1 plus e to the a capital delta squared minus 2 capital delta xf minus x tilde 1 plus, now let me go below, we have minus 2. This minus comes from the fact that I can write the cosine of this plus pi over 2 as minus the sine of this. So that's where the minus comes from. I can I have e to the a xf minus x tilde 1 minus delta squared, and then I have the sine of b delta squared minus 2 delta xf minus x tilde 1. And here I have to pay attention on how to close these brackets, but you have the idea, right? This bracket here closes this one, whereas this one is closed by this one, and this one is closed by this one. So it seems okay. And we are ready to write down, this is the final formula. I already wrote the formula on my Matlab script, and I want to show you the result. What we get, we get a curve, a probability curve. But in order to do that, I also have to introduce, the values. for these parameters. And remember that the parameter a can be written as minus 4 sigma squared divided by 4 sigma squared plus 2h bar tf divided by m squared, and then I have b equal to 2h bar tf divided by m divided by 4 sigma squared plus 2h bar tf divided by m, and this is squared as well. Now we make some assumptions for the values. We assume that sigma is equal to the width of the slit, delta. You can choose in principle other values for sigma, not necessarily equal to delta, but it's quite easy or intuitive to think of this in this way. So the standard deviation of the two Gaussian distributions that we have around the two slits are exactly equal to delta, the width of the slit, for simplicity. And I choose this value to be 3 times 10 to the minus 5 meters. So they are very small slits. And then I have capital delta. Remember that this is the distance between the two slits, and this should be a larger, it should be a number which is larger than this lowercase delta. And I will choose it to be 10 to the minus 3 meters. Then I choose the mass of the particle, which is the mass of the electron. I think of the particle as an electron, which is of the order of 9 times 10 to the minus 31 kilograms. And then I have, of course, the reduced Planck constant, which is of the order of 10 to the minus 34. And here we have its standard units, joules per second. And then I choose the final time TF because it also appears in the formula. And we assume that it will take around 10 to the minus 2 seconds for the particle to reach the wall. So TF is the time taken from the plate with the two slits to the wall. These are just some numbers, but I have prepared a script with the numbers, and I've also chosen the parameter x1, which is the position, the center of the first slit, which appears in this formula. So you can choose whatever value there because it is just the coordinate x1. I chose x1 x tilde 1 to be minus capital delta over 2, and this is a choice because it means that the other center x2 will be at delta over 2, capital delta over 2. So there is some symmetry over the x-axis with respect to the origin. One slit is at minus delta over 2 and the other one is at delta over 2, the centers of the two slits. And all the other parameters are the ones that I have given you here. I have calculated A and B, and then I have calculated the probability with this formula here, which is just this one. And I have normalized the factor of b squared to 1 for simplicity. So we will get a non-normalized probability when I do the calculation, but that's not really important. So if I run the script, this is what I get in this case for the probability. We can see that there is some interference pattern because at some points you can see that there are some minima, and it means that it is unlikely to find the particle there. Whereas where you see the maxima, it means that it is very likely to find the particle there. And this is exactly what the double-slit experiment tells us. It tells us that there are some interferences that appear, but those interferences depend on the shape of the slits, the width of the slits in particular, and the distance between them. And if we choose other parameters, for example, an important parameter is the distance between the slits, this capital delta. Because if we choose the two slits in such a way that they are very far from each other, so if they are very far away, so it means that delta is quite large with respect to the way that these waves oscillate. Well, we have to expect that there is no interference between the two waves, right? And we should see no interference pattern on the wall. And that's exactly what happens. For example, if I multiply this capital delta by a factor of 10 squared, which means that the overall delta is 10 to the minus 1, so we have pushed away the two slits, so they are further away with respect to before. Well, if I run the script in this manner, you can see that we only have two maxima of the probability, which are picked at minus 0.05, and the other one is of course at 0.05 if we check. Yes. And what is 0.05? 0.05 is equal to 0.1 divided by 2. And 0.1 is, of course, capital delta. So it means that in this case, the particle behaves in a classical manner because there is no interference. And indeed, classically, there is no interference between the particles. So it can either move through this slit and reach the screen or the wall, whatever, and it can move through this slit and reach the screen, like this, right? So there is no interference in that case. And I think that that's it for this video. I wanted to show you some details, some interesting, in my opinion, interesting details about the double slit experiment through the lenses of path integrals.